Okay, time to get started. Let's see here. Two quick things before we get into the math. One is, don't forget about the attendance quiz, right? So again, I'm going to make these announcements increasingly frequently going forward. But this appears in a minute and a half, so make sure to get that in. Secondly, I'm aware of the temperature of the room. It's not actually as bad as it was this morning. So I think maybe the AC is actually doing a little something. But it is what it is. I think there's something wrong with it. I have sent in a maintenance request, and so I think sometime in the next 6 months it will be good. I don't know. I can't speak to the schedule, but we'll see. Fingers crossed. Maybe, hopefully, they'll make me look bad and show up this afternoon. We'll see. Okay. So back into the math. So starting with section 2.5, chain rule. Y'all remember the single variable chain rule. I'm not gonna. I don't feel like I need to teach y'all the single variable chain rule. That said, I am going to talk about the single variable chain rule for the purposes of setting up a very particular point of view on it. Because that point of view is something that is going to very naturally extend to the multivariable setting that we're actually interested in. So if this is not, your personal favorite point of view on the chain rule, cool. Fine, but we need to understand this anyway so that we can make the extension. Okay, so here's the big idea. Y'all remember, I'm sure, that one way to think about a derivative is it's what you multiply by an input velocity to get an output velocity. And, this might be one of the sort of the undersold points of view on a derivative from a single variable calculus, but it's certainly true. It works. And y'all have heard me talk about this kind of thing quite a bit, at least in the multivariable setting so far. So it's a factor that you multiply by the green to get the blue, you might say. The key word here is factor. It is a multiplicative factor in going from green to blue. All right? Okay, now with that in mind, here's a composition of functions. By the way, there's various equations that I have written down here. You can largely ignore those equations. I'm going to be focusing on kind of a more of an intuitively satisfying take as opposed to the algebraic details. So, okay, here is a single variable function. X is the input, Y is the output. Here's another single variable, There's another single variable function. Y is the input and Z is the output. And then there is a third single variable function, namely the composition. The composition that does like this. And it takes X as the input, gives Z as the output. It's the sort of the doing F and G together all at once as a single function. Okay, all right. With this in mind, keep in mind, derivatives are multiplicative factors, right? So what is f prime? F prime is, I'm going to say, let me draw this a little bit differently. F prime is that factor. Likewise, where's G prime on this picture? Well, G prime is this factor. Okay, now, what about the composition? This, G compose F. In other words, do F first and then G. Where is the derivative of that composition on this picture? Well, derivatives, the way we're talking about them here, are multiplicative factors. And so the derivative of the composition here is what you multiply by that to get that. Right? dz dx, you might say. So, okay, all right. Well, now let me just. Here's a silly question. If I give you some number, it doesn't even really matter what the number is. And if I tell you, okay, now multiply it by 2, and then okay, now multiply the result by 3. Altogether, you've multiplied by 6, right? So the point being, factors multiply. So if we've got some x prime, whatever x prime might happen to be, if I multiply by the green and then multiply by the blue all together, in other words, what is the purple? I've multiplied by green times blue. It's that easy, right? Factors multiply. And so writing this down algebraically, and yeah, I've got a bunch of equations, and if you really don't believe my intuition, you can take the equations and plug in. It just gets a little hairy. It's just plugging in, but it gets a little bulky. Let's say that. The punchline, factors multiply simply tells you then that this factor is the product of these two factors. Simple as that. Does everybody buy it? Okay. I think that's very satisfying. This is one of my favorite takes on the chain rule. For whatever it's worth, keep in mind that viewing z as a function of x is a composition. And when I'm talking about its derivative, we get a product of the individual derivatives. So one way to say this is that differentiation turns a composition into a product. I'll come back to that in a bit. Okay, yawn, single variable calculus. You already knew all of this. Maybe this particular take is new, perhaps, but it's a bunch of familiar ideas. Here's the beautiful point. We can do all of those exact same arguments in a multivariable setting. The only difference is that now the velocities are vectors. Well, let's say two or higher dimensional vectors, as opposed to scalars, in other words, one-dimensional vectors. So all the same stuff works. What is a derivative? Well, again, many takes, but one of our big ones is it's what you multiply by the input velocity to get the output velocity. In other words, it is a multiplicative factor, just like in single variable. Same thing, right? It's just that now the input velocity and output velocities are vectors. Okay, yeah, totally. Now the factor is a matrix instead of a scalar, but it's still a factor. It's something that you multiply by. Okay. I can still talk about composing two multivariable functions. So here's a multivariable function. The x variables are the inputs, the y variables are the outputs. Yeah, now there's two inputs and two outputs, but whatever, it's a function. And then here's the second function. The y's are now the inputs. The z's are the outputs. And yeah, again, there's now two each. And then I can still talk about the composition that takes the x's as inputs and gives z's as the outputs. So you note the analogy, right? It's very, very similar to the setup we had in the single variable case. And the argument I'm going to make is, again, correspondingly analogous. How does df show up on this picture? Well, df is a multiplicative factor that you multiply by x prime to get y prime. Let's see here. dg shows up on this picture as, well, it's the multiplicative factor here that you multiply by y prime to get z prime. And where's the derivative of the composition on this picture? Well, it's the multiplicative factor you multiply by that to get that. And so I'm going to make the same case. If whatever you start with, I don't even really care what you start with, this x prime, or whatever. If you multiply by the green matrix, and then you subsequently multiply by the blue matrix, altogether, you have multiplied by the product of those matrices. Factors multiply. Right? And so we get the analogous conclusion. We have to write it a little bit differently because we have different notations between single and multivariable. And I don't know why I'm doing full screen mode. Let's get into... Oh, come on. Let's see. There we go. The derivative of the composition is the product of the individual factors. It's green times blue. Just like in single variable. Right, now again, in single variable, these were scalars, but yeah, scalar factors multiply, I mean, same story, and now they're matrices, but still factors multiply. How we doing? Everybody buy it? And again, there's a bunch of algebra on the page, and if you want to write all of this down and not leave any steps out, etc., then okay, sure, the algebra on the page is what you get. But morally, like, what's the takeaway? Where is the satisfaction? Not why does this work, but why should this work? This should work because factors multiply. I think that's really the best way to think about it. Okay. So what we have here, this is a big result. This is the multivariable chain rule. You might call this the matrix form of the multivariable chain rule. There's another form that I'll show you later. Ultimately, the other form is what I'll call a narrow special case of what I think is really the best form is this matrix form. Okay, now there are a couple little details I have to talk about. First of all, I claim that this works for any combination of dimensions. Notice what I drew here in the picture. Everything was two-dimensional. We had a two-dimensional X world, we had a two-dimensional Y world, two-dimensional Z world. Let's suppose, what if the Y world were three-dimensional? How would that change the argument? The answer is not at all. Not one bit. Right? The derivative matrix, this green derivative matrix would be a different shape matrix. Sure. But it remains that matrix is what you multiply by a two-dimensional input vector to get what would, I suppose, be a three-dimensional output vector. Right? So it would just be the corresponding shape matrix. And then likewise, the DG matrix would be a different shape. But ultimately, the point is you've still got two factors. The factors are matrices, and factors multiply. So it doesn't matter what the dimensions are. Don't sweat that. The other thing that's subtle I want to talk about. Let's go back to this picture here. And again, I claim that the derivative matrix is a factor. So df is the factor, but wait a minute, df evaluated where? Right, df is a matrix made up out of partials, which are functions. We have to know where do you want to evaluate them to get an actual matrix of numbers that you can actually multiply. And the answer, I hope this is pretty believable, but the answer is in all cases, where you apply the matrix is, well, where you are. Right? So this is a situation where we're, at the point A, and at this point A over here, we're entertaining the possibility that, hey, maybe if I start moving with some velocity, then my image over here will be moving with some velocity. And the DF matrix, well, I am here, and so I evaluate the DF matrix here. Is that cool? Reasonable, anyway? So now with that in mind, let's come back to the matrix form of the chain rule and notice there is a little subtlety I kind of swept under the rug. Two of the three of these matrices are evaluated at A. What's going on here? Why is DG evaluated at F of A, not at A? Well, let's look at what DG does. DG multiplies by that input velocity to get this output velocity, and it is evaluated where we are when we're, moving with velocity y prime in y world, and where you are is not A, it's F of A. Does that make sense? Everybody happy with that? Okay, good deal. Okay, and so again, I like to point out differentiation here has turned a composition into a product. So when you compose multivariable functions, you multiply the corresponding derivative matrices. Okay, let's do one. Let's get our hands dirty. Here we go. Now I have deliberately not given you the functions. We've got a couple of functions here, f and g. We're going to be composing them. See that what the question is asking is that we look for the derivative of the composition. So we're going to be composing these functions. Notice I have it set up very conveniently and appropriately where f takes x's as its inputs, gives y's as its outputs. What comes out of f is what goes into g. That's how compositions work. And then what comes out of the g function I'm calling the z's. Okay. All right, so this is set up just like on the previous page. Now, I'm not telling you what these functions are, but I am going to give you some information. I'm going to give you one value of the function and then a couple of values of the derivative matrices. It's not immediately clear when or where we'll need these, but that's given. So anyway, keep that in mind. Okay, so the question, derivative of the composition. All right, well, we've got a rule for that. Matrix form of the chain rule, right here. Derivative of g compose f, derivative of g times derivative of f, evaluated at the appropriate points. Okay, so we write that down. And therefore, the thing that we're interested in, right? Well, apparently one thing I'm going to need df at 1, 2. Oh, I'm given df at 1, 2. Boom. Yeah. Okay, let's see here. Now I'm also going to need the second derivative matrix. I'm going to need dg. Hang on. I need dg evaluated at f of 1, 2. Wait a minute. F of 1, 2 is where this dg that I'm given is evaluated. It just wasn't written that way, right? But 310 is f of 1, 2. And so this dg at f of 1, 2 that I need is the dg of 310 that I have. And boom. And then you multiply. Y'all know how to matrix multiply. And we get that. How we doing? Everybody happy? All right. Now that was the first part of the question. You'll notice there is... Oh, you know what? Before I go on, I do want to point out a little tricky thing here. The question asked for a derivative of g compose f. The form of this matrix form of the chain rule we have was written as g compose f. Sadly, not every pair of functions that you are given will be called f and g. And even if they are called f and g, you won't always have them in this order. It may be that you'll want to compute the derivative of f compose g instead of g compose f. Right? Who knows? The world's crazy out there, right? So you can't predict what form it's going to come in. So heads up about that. And do be advised, not everything looks the way it should, right? So on the one hand, f acting first is on the left in the diagram, but it's on the right in the composition, and its derivative is on the right in the chain rule. G, which is on the right in the diagram, is on the left in the composition, and its derivative is on the left in the chain rule. So it's easy to get these backwards. The only solution to this is heads up, right? Try not to think in terms of left and right. Try to think in terms of first and last, right? And it just happens to be, when you're drawing a diagram, the way we draw diagrams, first is on the left, because diagrams go left to right. And when you're multiplying matrices, first is on the right, because that's the one that will act on a vector. Vectors are on the right. So that's the one on the right is the one that's going to act on the vector first. So it's opposite, so sort of, left, right, opposite. And then likewise with composition. So make sure to keep all that straight. It's easy to mess it up. Okay. Yeah, so let's look at the second part of the question now. Second part of the question says what is this particular partial derivative. Notice it says partial with respect to x1. There's x1. It's specifically the partial of z3. There's z3. And so the way we're going to, let's see, how are we going to figure out that partial derivative? I don't have the formula, but I can immediately notice this is a partial derivative of the composition. I have the derivative matrix of the composition. So I know this partial derivative I'm looking for has got to be one of these elements. And also, don't forget, inputs correspond to columns. X1 is our first input variable, so we're going to be looking in the first column of that matrix. Likewise, don't forget, outputs correspond to rows of a derivative matrix. You're looking for the third output partial derivative. You're going to be looking in the third row of that derivative matrix, and then what you're looking for is that number right there. How we doing? Everybody good? All righty. Good deal. Okay, couple of special cases, and I'm going to be really quick with these. Y'all can, in fact, totally just read these yourselves. But again, I like to hit the highlights. What's the key point here? The key point in this first example is let's consider what happens when you have only a single input. Like your original, sort of the original input is just one-dimensional. Well, inputs correspond to columns. And so for this function, the derivative matrix has a single column. And for this function, the composition, the derivative matrix has a single column. Note also, both of these, the green and the blue functions, give position in one or the other of these spaces as a function of one parameter, let's call it time. Position is a function of time. These are parametric curves. And the derivative matrices, likewise, are velocities. So the takeaway, this special case, when you have that orange special case, let me actually, so the special case is there's just one original input. Effectively what you have is the chain rule becomes a statement about how the derivative matrix of f relates input velocities to output velocities. We already knew that. Right? So I think it's kind of cool when this happens that you have a big, powerful tool, and one of the special cases is something you already knew, which you can say differently as because of this observation, we can view the chain rule as a kind of a generalization of this old fact about derivative matrices. Right? This old fact about derivative matrices being as it is just a special case. Okay, for your consideration, notice this example that follows is it's straight out of this observation. Let's see here. Can I fit this all onto the screen? Yeah, here we go. So the question gives us an input velocity, and it asks us for an output velocity. And how do we take an input velocity and figure out how do we take an input velocity and find the output velocity? We'll multiply by the derivative matrix. Right? So this is just straight up just doing what we already knew how to do. And this example literally could have been an example in section 2.3. I've actually entertained lifting this example and taking it back into section 2.3, but pros and cons. Okay, so just an observation. Second observation, equally sort of like no big deal. If, in addition to having only one original input variable, if you also have only one eventual output variable, outputs correspond to rows of derivative matrices, and so we have here a single row. And of course, when you have a single row, multiplying by the derivative matrix is equivalent to dotting with the gradient vector. So again, we've talked about that a couple, 3 times in the past, and so this is just yet another instance of, don't forget, if you're talking about a real valued function, a derivative matrix is morally a gradient vector. All right, and so again, example, and again, this example could have come straight out of section 2.3. Okay, now I'm going to give you a different point of view. I want to emphasize, I really, really, really do think that that this is the best point of view right here. This is it's the most powerful form of the chain rule that we're going to see in this course. Certainly, there is a point of view that says this is the simplest form of the chain rule. Factors multiply. Right? It's if you see things the right way, if you have the scenario set up appropriately, that's all this is saying, is that factors multiply. It's a very digestible, believable claim. That said, big machinery. Right? Derivative matrices are these big, bulky things, and sometimes what you want is a very narrow, small, particular thing, and so sometimes this is just too big of a tool for what we need. So here's the alternative take. Suppose you have an original, sort of a first function and a second function, and now let's take a moment to recognize, as required for a composition, what comes out of the first function is exactly what goes in to the second function, right? That's how a composition works. I've got everything set up, so, Taylor set up for being a composition. And having done so, here's the chain rule. This is the matrix form of the chain rule. Notice I've got, let's see here, I have the derivative of this function here, made up of the partials of y's with respect to x's. And I've got the derivative matrix for this here. That's got the partials of the z's with respect to the y's. And notice I have the derivative of the composition here. That's got the partials of the z's with respect to the x's. So nothing happened. All I did here is expand the matrix form of the chain rule. And let's suppose this little thing right here is all I want. I don't need any of these other elements. I don't care about the partial of one other output with respect to one. I just want to just one partial derivative is all I need. Well, of course, y'all know how to compute a single element of a matrix. Corresponding row there, corresponding column here. You dot appropriately, so you have these elements get multiplied by those elements. You sort of multiply and add, dot product, old news. And that tells you this one element that you're interested in. So what this gives us is an alternative version of the chain rule. This is kind of a coordinate version of the chain rule. Pros and cons. Good thing gets right on to what you're interested in. If you're interested in just that one partial derivative, boom, we're getting right to it as efficiently as possible. The bad news is it's a great, big, long, complicated formula set up in terms of variables that probably won't be set up that way when you need to apply this in practice. So this is, I'm going to call it clunky. Why does this work? Well, it's further discussion, right? I mean, it's not something that you can just look at and say, well, factors multiply. So I hope this will not be your primary take on the chain rule, but it is a take. And I'm going to give you a different way to think about it in a couple seconds. First thing I want to do is give you a massive warning. This is super dangerous. It's really dangerous. I've seen so many students mess this up, get wrong answers, but worse, because they applied wrong reasoning, and that's where you really lose points, right? So in particular, I have seen lots of students say, okay, partial of zi with respect to xj, well, that's going to be Let's see here. Here's my first term, zi with respect to y1 times y1 with respect to xj. Oh my God. These cancel, and the denominator is what it's supposed to be, and the numerator is what it's supposed to be, and then they just put a box around this and scratch off or never even think to write down all of that, and then they just declare victory and walk away. Does everybody see the temptation? It's very tempting. It's super wrong, right? Now, why do I know it's wrong? Well, I know it's wrong because we already derived this formula. These terms are there. That's how matrix multiplication. If matrix multiplication worked like this, linear algebra would be very, very different, right? So these terms have to be there. This argument is not giving us the valid result. So this is disturbing. Let's ask them the more difficult question. I understand that this is the wrong answer, but what is wrong with the reasoning? Right? There's got to be something wrong with the reasoning. It's subtle. What's wrong with the reasoning is at the very beginning when I said that, I'm just going to cancel these. Yeah, they're not the same. Those are not the same things. And I'm sorry, I know the notation makes it look like they're the same thing. They're not the same thing. The notation is, golly, I don't want to say I don't like it because I don't have a better idea. Any notation that I could think of that would remove this confusion would be extremely bulky and uncomfortable, and you would have many other reasons to not like it. But nevertheless, these things are different, and we write them as being the same. I think the best way to think about this scenario is that this thing by itself, partial y1, full stop, just partial y1, not a thing. It is not a well-defined thing at all. Okay. So let me walk you through what I'm talking about. Why are these things, I claim they're different, in what way are they different? Well, let's think about where these are, where they come from. What is this partial y1 here? This is part of a story. The story is that I'm looking at the variable zi, and I want to know how it changes as y1 changes, and so I hold all of the other y's constant, and then I allow y1 to change a little bit, and then I ask how much zi changes correspondingly. So there's a scenario there. There's a premise. It's like a little story. In that story, all the other y's are constant. All right, now let's talk about what this partial y1 is. Well, it's part of a different story. In this story, xj I'm treating as a variable. The other x variables are being held constant. But here's the thing. If the xj's are changing, all of the y's are changing. All of the y variables are functions of xj. You change xj, you're going to be changing all of the other y variables. So, different story. Right? So the way I like to say this is, let's see, and I think I got this right, but correct, if I get the movies wrong, please correct me. But there's a character named Harry in the Spider-Man movies, I'm pretty sure. Isn't that right? Okay. And there is a character named Harry in the Harry Potter movies. And they are not the same. Right? Two different stories, same name, different characters. Of course they're different characters, they're different stories. Don't be silly. That's what this is. Right? Two different stories, these characters have the same name. They're not the same characters. Is everybody with me? Okay. So this is a tempting thing. You can see the temptation. You're going to so want to do that. And cancel them both. And that's nonsense. And it betrays a fundamental misunderstanding of what's going on. So don't make that mistake. Does that make sense? Okay. All right. Okay, so how do you think about this? This is my favorite way to think about it. Let's suppose we are interested in partial of zi with respect to xj. It's a partial derivative, which means, of course, that all these other x variables are going to be constants. We're going to treat those as constants. And here's what happens if you leaving all these other variables to constants. If you let xj change a little bit, if you tweak xj, well, I mean, all of these y variables, they're all functions of xj. If you change xj a little bit, all of these y's are going to change by some amount. And here's the other thing. Individually, each one of these y's, upon changing, will contribute to some change in zi. Zi depends on, for example, y1. However much y1 changes, that's going to cause some corresponding change in zi. But y2 changing will also contribute to changes in zi, and on down the line. And the ym, upon changing a little bit, will contribute to a certain amount of change in zi. So the way I like to think about it is there's various different paths along which changes can propagate from xj to zi. Right? And for each path, there's a corresponding term. Now let's ask, what is the term for this first path? For this first path, well, let's see here. Per unit change in xj, how much does y1 change? Boom. Okay, per unit change in y1, how much does zi change? Bam. Right, so all together, this term, the term that I'm highlighting here in purple, that term tells you how much changes in xj propagate through y1 to cause changes in zi. This term corresponds to this path of propagation. And likewise, for every other path, there's a corresponding term, right? So this path gives rise to this term, and then likewise, et cetera, this path gives rise to that term. So I think it's a nice way to think about it. You get a term for every path. And by the way, I'll further note, every term corresponds to a path. Every path corresponds to what we call an intermediate variable, because of course, it's in between. So this sometimes referred to as thinking about the chain rule in terms of intermediate variables. Everybody buying it? By the way, here's some good news. These terms, what do they look like? Well, whatever your intermediate variable is going to always go there and there. Whatever you're taking a partial of will always be there. Whatever you're taking a partial with respect to will always be there. The structure of these terms is always the same. Everybody happy? Okay, so this is a great way to think about it. I'm a big fan. In these circumstances where you only care about one single partial derivative, let's do one. Let's see here. We're going to look at this scenario here. We've got an f, we've got a g. Let's. By the way, let's not try to take advantage of the fact that we know what these functions are. I'm going to remind y'all of one of the sort of the philosophical points of how tests work in this class. It's not about answers; it's about reasoning. Right? Every question has a purpose. The purpose will always be, I want you to demonstrate your proficiency with a certain either idea or method, concept, whatever piece of relevant material from the class. And so you should always approach test questions from the point of view of, okay, what's this about? What am I supposed to be demonstrating proficiency with? And then make sure in your response that you demonstrate the right proficiency, right? So on a question like this, if you were to take these formulas for y1 and y2 and plug them into this g function and get a great big monstrosity single variable function of z2 in terms of x2, and then take a single variable derivative, it's missing the point of the question, right? The question's clearly about, hey, we've got a composition of multivariable functions. The clear intention of this question is, I wanted to see that you can use the multivariable chain rule. So make sure to actually, satisfy the intention of the question. Again, it's not about the answer. The fact that you get the right answer, it's not what the course is about, right? I want to see that you can demonstrate the right ideas. So I hope that makes sense. If you're not sure you follow, or if you're not quite clear on any of that, do come talk to me anytime. I'd be very happy to expound, clarify, whatever on that point. Again, really important. Okay. I strongly suggest setting up a diagram. This is how you can keep track of what goes where and what variables play what roles and which variables are intermediate variables, for example. We're going to need to know that, right? So notice the inputs to the first function I've got here. The outputs from the first function, aka the inputs to the second function, I've got here. Because that's how you compose. And then the eventual outputs, the outputs from the second function, I put here. So now I've got my diagram. With my diagram made, notice we're taking a partial of z2, there it is, with respect to x2, there it is. Now the diagram is doing tremendous work for me. The diagram is telling me exactly where the paths are. There is that path, which you might call the y1 path. And check it out, here's the y1 term. Right? And then I can see, again, thank you diagram, the y2 path. And here is the y2 term. Right? And it follows each one of those terms follows the pattern of what all terms look like. And so, tailor-made for this specific scenario, all I had to do is write down a diagram, think about paths, and I have a tailor-made chain rule. Perfect for the exact situation that I have, and then it's a matter of taking partial derivatives, plugging in some numbers. Y'all can do that. How we doing? Okay, so this is a very strong, urging advice when you have a bunch of algebra given to you. Now, by the way, I was generous in how I wrote this down. I set up that. I mean, the order of the variables was in alphabetical order. Wasn't that nice of me? All of the variables at each stage were using the same letter. Life isn't like that, right? So this can be really, really hard to keep track of in general. The diagram will do that for you. Don't try to keep track of all that in your head. It's just a bad plan. If nothing else, then you're not communicating your thoughts, right? So I think the diagram, I urge that you write a appropriate diagram to explain what you're doing. Okay, confusion of variables. This is a silly observation, but this will get you out of a lot of trouble that you can accidentally get yourself into. Here's a silly single variable calculus example, right? Two functions. When you compose, how do you take the derivative? Now let's cheat first. The composition is x to the sixth. We know what the derivative of that is. It's 6x to the fifth. Right? So let's go into this with knowing what the right answer is. And here's the wrong, casual, sloppy, careless take. I'll write down that the derivative of composition is the product of the derivatives. Kind of has there's an element of truth to that, right? But then you write down the individual derivatives, and then you multiply them, and you don't get the right answer. Right? Okay, what did we do wrong? Well, we were a little too sloppy in how we wrote this down. The right way to write that down, you have to remember the derivative of the second acting function is evaluated at the output value of the first. function. Right? So that's what I screwed up. Up here where I had an x, I should have put f of x, namely x squared. So that was my mistake, and you can see you can fix that mistake and get the right answer. But even this, I think is pretty confusing. Right? This analysis right here leaves g written as a function of x. Let me explain why I think that stinks. That absolutely stinks. If I write f as a function of x, let's just ask, what should I call that output? Can I call that output x? No. That would be ridiculous, wouldn't it? If I called the output, the input's x, I can't call the output x. Nonsense. Well, what comes out of f has to be what goes into g. So if you're going to call the output from f, let's say y, you really should rewrite g in terms of y. Everybody see that? Otherwise, you're committing what I would call confusion of variables. Well, just don't do that. There's no reason to do that. Why would you do that? There's nothing to be gained from doing that. You're just creating your own landmines to step on. Right? This is a silly mistake. So rewrite the function. Now this is the exact same function. Can't emphasize this enough. This function and that function are still the same function. That function g is the function that cubes whatever you give it. And whether you phrase that in terms of a dummy variable called x or a dummy variable called y or a dummy variable called Bob, it doesn't matter. It's whatever you give me, we're going to cube it. Right? So who cares? So don't lose any sleep over, oh my God, is this the same? Am I cheating? Am I allowed to do this? Yeah, right, in terms of whatever variable you like. Right? Okay. And then look how easy the problem becomes. Be as careless as you like. Product of the derivatives, okay, sloppy, not indicating where anything's evaluated, and yet, when you write that down, you have this remaining y here that forces you to ask, hey, by the way, what is that y? And then you realize, oh yeah, y? Oh yeah, that's what comes out of the f function. That y is x squared. The notation that you've set up, simply not confusing your variables, makes it impossible to mess this up, pretty much, right? Okay. All right, so now again, that's all single variable, but it's the exact same idea with multivariable. I mean, it's really the same idea. Here's a perfectly reasonable question, perfectly reasonable function, whatever, perfectly reasonable second function, fine. There's nothing wrong with these functions. Until we say, hey, I want to compose them. And at that point, once there's an indication you're composing them, you should get uncomfortable. You should think, wait a second. F is written in terms of x's and y's. I can't call these outputs x's and y's. I'm going to call those outputs u and v. Or let's just say, right? And the very moment you decide to call those outputs u and v, you really ought to rewrite g then as a function of u and v. And so you take that, you just recopy it basically. And notice I didn't change the function at all. It's the exact same function. Nothing happened. I'm just writing it in terms of a different dummy variable so that I'm not committing a confusion of variables. You do that one little thing, and now again, be as careless and slapdash as you like. Derivatives, right? Multiply. And then you just notice, wait a minute. What's the deal with that u again? Where did this u come from? What am I supposed to do with that u? Oh yeah, u is the first input to g. Therefore, u must be the first output from f. Boom. And then likewise for b. Everybody happy? Okay. let's see, now where are we at? Yeah, you know what? This is actually a pretty good stopping point, and it's Friday. Why don't we stop 30 seconds early? See y'all later. Have a good weekend. Okay.